In the quiet stillness of tonight, welcome gently to the Sleepy Science Channel, a peaceful corner of the universe where we drift together through the boundless wonders of the cosmos, a place so vast, so ancient, and so profoundly mysterious that even the greatest scientific minds can only grasp faint shadows of its true enormity. For beyond our familiar solar system lies an ever-expanding ocean of darkness illuminated by countless stars, each one a blazing sphere of nuclear fire, each one a tiny spark in a sea that stretches farther than human imagination can reach, and for billions of years, far longer than any civilization or life form has existed, entire planets, stars, moons, and galaxies have been born, reshaped, and destroyed in an endless cosmic cycle that unfolds silently across unimaginable distances. Astronomy allows us to witness small glimpses of these miracles, revealing collisions of stars so powerful that human language struggles to describe them, revealing rogue planets that wander alone with no sun to warm them, revealing invisible forces that warp the fabric of spacetime itself, bending reality into curves and spirals, and showing us ancient galaxies formed when the universe was young, colossal black holes that seem to mock the laws of physics, and countless wonders still hidden in the shadows, waiting patiently to be discovered by future explorers. As you settle into comfort, letting your breath soften and your thoughts drift like dust through sunlight, imagine yourself floating gently through this vast cosmic darkness, unhurried and unburdened, watching the universe unfold in slow, dreamy motion. Imagine a massive star reaching the end of its life, its brilliant energy finally diminishing after millions of years of burning fiercely, and as its nuclear fuel runs out, its core loses the strength to resist the crushing pull of gravity, collapsing inward with breathtaking speed, compressing matter into an impossibly dense state, until suddenly the collapse rebounds outward in a titanic shockwave that races through the dying star's outer layers, blasting them into space. The explosion becomes a supernova, a single event so radiant that it can briefly outshine an entire galaxy containing billions of stars. And in that dazzling flash, heavy elements like gold, silver, iron, and carbon are created and thrown into the universe, drifting through space for eons until they join clouds of gas and dust, eventually becoming part of new solar systems, new planets, and perhaps even new living beings who will one day look up and wonder about the origins of the atoms inside their bodies. Now picture planets born in young star systems where gravity shapes chaos into order, where dust and rocks collide endlessly, sticking together bit by bit until large worlds emerge. But where gravitational battles between worlds can become so violent that a planet may be flung outward with incredible force, cast loose into the silent darkness between stars, becoming a rogue planet drifting through the galaxy alone, its surface frozen beneath eternal night, receiving no warmth from any nearby star, yet possibly still warm deep inside from ancient heat or radioactive decay. Imagine thick atmospheres swirling above these cold, lonely worlds, trapping heat. Or perhaps oceans buried beneath global ice layers, warmed by geological forces and filled with slow, secret chemistry that never sees starlight, allowing the possibility that even in the deepest darkness, somewhere far from any sun, nature might still find a way to create complexity, then drift closer to a spinning black hole, a place where the universe behaves in ways that defy all common intuition, a place where a collapsing star has left behind an object so dense and so compact that even light cannot escape its gravity. But imagine a black hole spinning rapidly, dragging spacetime itself around with it like water swirling down a drain, twisting everything nearby into a spiraling dance. In the region near the black hole known as the ergosphere, space is pulled so strongly that nothing can remain still, and in this strange, warped environment, energy can actually be extracted from the black hole's rotation, fueling enormous jets that shoot out into space at nearly the speed of light, stretching across thousands of light years and shaping the behavior of their host galaxies over millions of years. Now drift back toward our solar system, where beneath the frozen surfaces of certain moons, such as Europa around Jupiter or Enceladus around Saturn, lie vast oceans deeper than any found on Earth, oceans sealed beneath ice sheets that may be tens of kilometers thick, oceans warmed not by sunlight but by tidal forces, where the moon is squeezed and stretched by the gravity of the planet it orbits, generating heat deep within its core, Imagine hydrothermal vents on the ocean floor releasing warm, mineral-rich water into the surrounding darkness, creating environments that could support complex chemistry and possibly even life, completely isolated from the surface and untouched for billions of years. Now lift your gaze to the largest structures in the cosmos: galaxies. Enormous collections of stars, gas, dust, and dark matter, moving through space not as static objects but as travelers subtly pulled toward one another by gravity, and as they approach, their shapes distort, stretching out long tidal tails of stars and gas that arc gracefully across space, while massive clouds of gas collide and compress, igniting bursts of star formation, creating clusters of newborn stars that glow brightly in the cosmic night, until eventually, after millions of years, the galaxies merge into a single, massive, more rounded structure, a new cosmic city of stars formed from the delicate gravitational dance of two ancient spiraling worlds. Between stars there exist strange objects known as brown dwarfs, too massive to be planets yet not massive enough to sustain the nuclear fusion that powers true stars. Objects that begin their lives warm and glowing, then slowly cool over billions of years, until their heat fades into a dim infrared glow. And clouds of dust and exotic molecules swirl through their atmospheres, creating storms and patterns unlike anything found on planets or stars, occupying a beautiful in-between state that reveals how diverse the universe's creations can be. Drifting through the outer reaches of solar systems are comets, icy relics from the early days of planetary formation, frozen time capsules carrying organic molecules created long before the sun existed, formed in the cold darkness of the primordial cloud that collapsed to create our solar system. As a comet approaches a star, its ice warms, releasing gas and dust that expand into a glowing coma and a long tail illuminated by sunlight. And by studying the light that passes through this material, scientists have found simple and complex organic molecules, carbon chains, nitrogen compounds, and other building blocks of biology, suggesting that the ingredients for life may have been scattered throughout the young solar system by comets billions of years ago. And finally, imagine drifting into a vast nebula. A glowing cloud of hydrogen, dust, and complex molecules, where new stars are born deep inside swirling pillars and luminous waves of gas, and when massive young stars ignite, they flood the surrounding clouds with intense ultraviolet radiation that strips electrons from hydrogen atoms, creating enormous volumes of ionized gas that glow in pinks, reds, blues, and purples, creating some of the most breathtaking and colorful sights in the universe. Sights so magnificent that even the most advanced telescopes can only reveal small pieces of their beauty. Within these nebulae, gravity slowly pulls material together, creating dense knots that collapse into newborn stars surrounded by swirling disks of gas and dust that may one day form new planets, moons, and comets, continuing the eternal cycle of cosmic birth and rebirth. And as you breathe softly and allow your thoughts to drift like stardust across a silent sky, let the immensity of these wonders soothe your mind. The drifting rogue planets, the shining supernova explosions, the spinning black holes, dragging space-time into spirals, the hidden oceans beneath frozen moons, the merging galaxies weaving starry threads across space, the cooling brown dwarfs glowing quietly in the infrared night, the ancient comets carrying chemistry older than the sun, and the luminous nebulae glowing like cosmic gardens where new stars sprout from clouds. Let all of it wash over you like a gentle wave until your mind becomes quiet, still, peaceful, and open to the wonder of the universe. Across the vast expanse of the cosmos, luminous regions formed by newborn stars spread across many light years, their glowing shapes sculpted by the delicate interplay of gas density, stellar winds, radiation pressure, and the unrelenting pull of gravity, creating scenes of breathtaking complexity where dark lanes of dust snake through radiant clouds, carving sharp silhouettes against brilliant backgrounds and reminding us that even light must bow to the presence of thick cosmic grains. Over millions of years, the combined influence of intense ultraviolet radiation, high-velocity outflows, shock fronts, and turbulent eddies generated by the embedded stars gradually erodes the original cloud, carving enormous bubbles, cavities, hollows, and branching tunnels through the gas, peeling away layers, dispersing vast quantities of material into surrounding space, and ultimately transforming the nebula from a dense, shadowed nursery into an airy, expanded region where the original structure survives only as thin filaments drifting across stellar light. And in other corners of the universe, extreme gravitational forces stretch planets into elongated, egg-like shapes whenever a world orbits dangerously close to a massive companion whose gravitational pull acts more powerfully on the near side than the far side, producing enormous tidal forces that ripple not only through oceans, if oceans exist, but through the very rock and mantle of the planet, twisting its crust, deforming its interior, and generating internal friction that produces intense heat. Over immense periods, this stretching reshapes the planet's entire figure, drawing solid material toward the line connecting it with its host star or companion object, so the planet becomes noticeably elongated, its longest axis permanently locked toward the massive body it orbits. And the constant flexing of its interior drives volcanic activity, tectonic motions, mantle convection, and widespread resurfacing, while its atmosphere, if it possesses one, reacts dramatically to this unusual geometry with violent jets, chaotic circulation, multidirectional winds, and temperature patterns unlike anything experienced on a nearly spherical world. Such distorted planets offer astronomers an extraordinary natural laboratory, allowing them to study how gravity molds solid matter under extreme conditions far beyond anything achievable on or near Earth, while elsewhere, pulsars emit perfectly timed beams of radiation that sweep through the sky like cosmic lighthouses, for these objects are the rapidly spinning, incredibly dense remnants of once massive stars that ended their lives in titanic explosions, leaving behind compact neutron-rich cores with diameters comparable to earthly cities yet containing more mass than the Sun, spinning at astonishing speeds, sometimes hundreds of times per second, and possessing magnetic fields trillions of times stronger than Earth's, funneling charged particles toward their magnetic poles and accelerating them to tremendous energies, causing them to emit focused beams of radio waves, X-rays, or even gamma rays. As the pulsar rotates, these beams sweep outward across space like the beams of a rotating lighthouse, and if one of these beams crosses Earth's location, we detect a perfectly timed pulse of radiation whose intervals remain stable with almost unbelievable precision, often rivaling or surpassing the best atomic clocks ever built by humans, enabling astronomers to probe theories of gravity, measure the distribution of invisible matter in our galaxy, search for gravitational waves produced by distant pairs of orbiting remnants, and study motions so subtle that they reveal shifts in spacetime itself. Meanwhile, gas giant planets brew storms larger than Earth that refuse to fade for centuries, towering tempests churning within colossal atmospheres made of ammonia, methane, hydrogen, helium, and even crystalline particles of exotic compounds that condense under crushing pressures and extreme temperatures, while deep internal heat rises upward and rapid rotation twists atmospheric belts into high-speed jets, causing layers of gas to slide past one another, generating shearing zones where turbulence grows, organizing itself into vortices of staggering size, each storm pulling in energy from the planet's hot interior, expanding across thousands of kilometers, rotating with monumental momentum, and persisting because these giants lack solid surfaces to sap their power, so their swirling shapes, colors, chemical signatures, lightning events, and evolving boundaries shift slowly over centuries as the surrounding bands supply or drain their strength. Each storm becomes a world unto itself, containing towering cloud tops, lightning-filled depths, swirling aerosols, temperature gradients broader than continents, and structures so immense that they dwarf everything on Earth, revealing that alien weather can operate under rules that differ dramatically from our own. And drifting far beyond these titanic planets, entire galaxies exist with so few stars that they appear almost empty. Faint ghostly systems in which only a sparse scattering of stars glows against the dark canvas of space. For these ultra-diffuse galaxies may have begun like ordinary gas-rich clouds, but environmental factors, interactions with larger neighbors, or early explosive bursts of star formation stripped or expelled much of their raw material, leaving behind only fragile remnants loosely held together by dark matter, their dimness revealing hidden clues about cosmic architecture, gravitational scaffolding, and the influence of ancient collisions and environmental conditions on galactic evolution. What remains in these sparse systems is a faint sprinkling of stars suspended in vast halos of dark matter, following the same gravitational rules that govern normal galaxies, and by studying their motions and compositions, astronomers trace the quiet history of forces acting over billions of years, uncovering records of cosmic events long finished. And as we move onward through this grand cosmic landscape, we encounter stellar remnants shrunk to the size of Earth yet incredibly dense, created when stars of moderate mass exhaust their nuclear fuel, shed their outer layers in ghostly planetary nebulae, and leave behind compact cores no longer supported by fusion but instead held up by quantum mechanical pressure, with electrons squeezed into mysterious collective arrangements impossible under ordinary conditions, forming white dwarfs that cool slowly over billions of years, radiating away stored heat as they fade into darkness. These remnants reveal the transition between active shining stars and the quiet final states that await many of them, offering glimpses into matter under pressures and densities that challenge the limits of laboratory physics. Moving deeper into the diversity of the universe, planetary systems sometimes develop worlds that orbit at bizarre, seemingly impossible angles, for although newborn systems begin with disks that appear flat and orderly, gravitational encounters with neighboring stars, passing objects, stellar flybys, or internal giants can tilt, twist, or destabilize entire orbital families, pushing planets into inclined, skewed, or polar trajectories. And once the geometry shifts even slightly, resonances and long-term gravitational interactions can amplify these misalignments, sending planets into orbits far above or far below the plane of their companions, creating systems that defy old expectations and demonstrating that early planetary development is sensitive, fragile, and easily reshaped by chance encounters. Each tilted orbit serves as a time capsule, containing clues about ancient events, scattered masses, migrating giants, passing stars, that are no longer visible except through the distorted architecture they left behind. Scattered throughout the solar system and beyond are metal-rich asteroids holding precious elements in concentrations far higher than anything found in Earth's crust. Fragments of ancient differentiated bodies heated in the turbulent early solar system, where heavy elements such as iron and nickel sank inward to form metallic cores before violent collisions shattered these primordial worlds, sending pieces drifting across space for billions of years. Today, these fragments, dense, nearly solid metal bodies covered with thin layers of dust or silicate, reveal the internal structure of early planets before collisions, migrations, and long cooling periods shaped the modern solar system, offering scientists direct windows into planetary formation, thermal evolution, and the violent processes that dominated the solar system's youth. Together, all these extraordinary phenomena, from luminous nebulae sculpted by radiation to planets stretched by tidal forces, from pulsars spinning with clock-like precision to gas giants generating storms older than civilizations, from ghostly galaxies shaped by ancient interactions to white dwarfs cooling in silence, from tilted planetary architectures to metal-rich asteroids preserving the memory of primordial worlds, form a single grand, interconnected story of cosmic evolution, a story written across billions of years and vast stretches of space, a story still unfolding quietly in the darkness, waiting patiently for curious minds to observe, interpret, and marvel at the endless creativity of the universe itself. Massive stars burn through their fuel with astonishing speed, living bright and brief lives when compared to the vast stretches of cosmic time, and although they contain enormous reserves of hydrogen and helium, far more than modest, sun-like stars, they consume these elements at a furious pace as their cores blaze with unimaginable intensity, generating vast amounts of energy that streams outward as searing light and heat. This immense output exerts a tremendous outward pressure that must constantly battle against the inward pull of gravity, creating a delicate and increasingly violent balance. The more massive the star, the more extreme this internal struggle becomes as the core heats to such high temperatures that it begins fusing heavier and heavier elements, eventually reaching a point where collapse is unavoidable. Smaller, gentler stars may shine steadily for billions of years, but these giants race through their existence in mere cosmic moments, and when they approach the end of their short, furious lives, they die in spectacular explosive events that reshape their surroundings, scattering the heavy elements forged in their cores across interstellar space, enriching the clouds from which future stars and planets will one day form. In contrast to these magnificent stellar titans, some planets appear deceptively small and gentle, yet reflect so much starlight that they shine almost like tiny suns themselves, their brightness caused by highly reflective cloud decks or surfaces composed of materials that scatter light with exceptional efficiency. These gleaming worlds may orbit extremely close to their stars, receiving a constant flood of illumination that keeps their atmospheres glowing and their surfaces shimmering, while minerals vaporized by intense heat can condense into glittering particles, creating layers of reflective haze that only enhance their brilliance, enabling astronomers to detect their presence even when the planets themselves cannot be seen directly, and allowing researchers to infer details about their atmospheres, temperatures, and orbital paths by studying their luminous signatures. Elsewhere in the universe, some regions contain magnetic fields millions of times stronger than Earth's, environments shaped by compact stellar remnants, dense clusters, or swirling torrents of charged particles interacting with intense gravitational landscapes. And as matter spirals inward toward collapsed objects, electric currents arise that amplify surrounding magnetic fields to extraordinary levels, creating invisible structures that channel particles along narrow paths and accelerate them to astonishing energies. These powerful magnetic zones sculpt the behavior of gas, dust, and radiation, influencing the formation of jets, the emission of brilliant flashes of light, and even the shapes of atoms themselves, which can be stretched and distorted under such extreme conditions. By studying the light emitted from these exotic regions, astronomers gain insight into the physics that governs some of the universe's most extreme environments, where heat, pressure, and gravity reach levels unimaginable on Earth. When light from distant galaxies travels through space and passes near immense galaxy clusters, the unfathomable mass concentrated within those clusters bends the very fabric of space itself, curving the paths of photons in a phenomenon known as gravitational lensing. This cosmic distortion can stretch, magnify, or twist the images of remote galaxies into elegant arcs, rings, or multiple reflected shapes, and by studying these patterns, astronomers can map not only the visible matter in the cluster but also the elusive dark matter that emits no light yet dominates the cluster's overall mass, creating a natural telescope that allows scientists to examine distant cosmic structures far beyond their usual reach. Even dying stars contribute beauty to the universe as they gently shed their outer layers, releasing gas into space in intricate shapes that appear sculpted with delicate artistry, with slow pulsations lifting shells of material outward and faster winds following behind, reshaping earlier layers into rings, bubbles, hourglass forms, or twisting filamentary patterns that glow in a range of colors depending on their elemental composition. These elegant structures, known as planetary nebulae, form during the final phases of a star's life, when internal rhythms, rotation, and magnetic fields interact to shape the departing layers, and as the central remnant cools and fades, the expanding gas gradually disperses into the galaxy, carrying enriched material that will someday help form new stars and planets. In vast, cold regions of the galaxy, enormous clouds of gas and dust drift in quiet darkness until something disturbs their stillness. A shock wave from a nearby explosion, the gravitational pull of a passing cluster, or the radiation from an earlier generation of stars, triggering subtle ripples in density that eventually cause the cloud to collapse under its own gravity. As the collapse accelerates, the cloud fragments into numerous dense pockets, each heating as material is drawn inward, eventually glowing softly as a protostar begins to form at the core while surrounding gas settles into a spinning disk that will shape the structure of the future planetary system. Over time, entire families of new stars are born from this single collapsing region, some massive and brilliant, some small and faint, many destined to orbit each other in graceful pairs or groups, and even after the original cloud disappears, these stellar siblings retain traces of their shared origins in their motions and chemical compositions. In planetary systems, orbits that begin in calm, orderly patterns can gradually evolve into strange, elongated shapes after gravitational encounters with massive neighbors. Even a small nudge during a close passage can increase a planet's orbital eccentricity, transforming a nearly circular path into a long, stretched ellipse. Additional gravitational tugs over millions of years can exaggerate the effect, creating orbits that carry a planet extremely close to its star during one part of its cycle, where it experiences intense heat, and far into colder, darker regions during another. Such orbital extremes influence climates, atmospheric chemistry, and geological processes in ways that can dramatically reshape the planet over time, and observations of distant planetary systems show that these interactions are common, each distorted orbit telling a story of ancient encounters and long-finished events that sculpted the planetary family into its present form. Near the centers of galaxies containing supermassive black holes, swirling disks of superheated gas spiral inward toward the event horizon, where gravity becomes so intense that not even light can escape. Yet before this material crosses that final boundary, magnetic fields and rapid rotation channel some of it into narrow beams that shoot outward as jets of particles traveling at nearly the speed of light. These jets pierce through surrounding gas, illuminate distant clouds, and extend far beyond the boundaries of the host galaxy, carving colossal paths through intergalactic space and heating material that might otherwise remain cold, serving as luminous beacons that reveal the hidden power of the compact object at their core. Meanwhile, within the quieter realms of planetary systems, some moons experience tidal heating so intense that it melts rock deep below their surfaces. As these moons travel along slightly elongated orbits around their parent planets, their distance changes during each cycle, drawing them closer at one point and farther away at another. This rhythmic stretching and squeezing creates immense internal friction, generating heat that can sustain vast subsurface oceans, drive volcanic activity, reshape crusts, and influence atmospheres. Across the universe, from the violet lives of massive stars to the reflective brilliance of unusual planets, from regions dominated by magnetic titans to the graceful distortions of distant starlight, from the sculpted beauty of dying suns to the quiet birthplaces of new stellar families, from the twisting paths of planets to the jets launched by cosmic giants, and from the tidal pulse of moons to the far-reaching influences of gravity and light, each phenomenon reveals a universe endlessly reshaping itself, governed by forces that span scales from the subatomic to the intergalactic. And within these vast interactions, each structure, orbit, and ray of light carries the story of countless events that have unfolded across billions of years, leaving behind traces that allow us to piece together the grand, intricate, and awe-inspiring tapestry of the cosmos. The changing distance causes shifts in gravitational pull that stretch and compress the moon repeatedly, and this constant cycle of expansion and contraction acts like a slow, powerful heartbeat deep within the moon's interior, generating steady friction in layers of rock, ice, and partially molten material that would otherwise remain locked in frigid stillness. And as this rhythmic flexing continues over hundreds of millions of years, the heat slowly accumulates, warming regions that would have been frozen solid, creating pockets where rock softens, cracks widen, and buried reservoirs of liquid water begin to form beneath the surface, sometimes gathering into vast oceans sealed under thick, ancient crusts of ice. In certain worlds, the internal pressure created by this heat becomes so great that plumes of vapor and icy particles erupt through surface fractures, releasing geysers that burst into space in shimmering fountains of material, while in other moons the heat is more subtle, gently driving slow currents within hidden oceans that circulate nutrients, salts, and minerals, creating environments where complex chemical reactions might unfold in the deep, silent darkness. These internal processes transform moons from inert frozen spheres into dynamic worlds sculpted from within, showing that even in remote, cold regions where sunlight cannot penetrate, the push and pull of gravitational motions can generate warmth, motion, and possibility far beyond what simple distance from a star would suggest. While these transformations unfold in the unseen interior of distant moons, ancient starlight makes a far longer journey across the cosmos, traveling for billions of years before finally reaching Earth, carrying with it faint but precious information about the earliest eras of the universe. When a distant star or galaxy emits light, the photons begin a journey through the expanding cosmos, passing through vast regions filled with galaxy clusters, cosmic filaments, and immense voids, and the gravitational pull of these structures can stretch, bend, or shift the color of the traveling light. Some wavelengths are absorbed by cold gas clouds drifting between galaxies, while others continue almost untouched through the darkness, eventually arriving at our telescopes as quiet messengers from the deep past. Because the universe is constantly expanding, The distance these photons travel grows even as they move, and by the time they reach us, the objects that release them may have completely changed or vanished, collapsed into black holes, merged with neighbors, or transformed through explosive events. The light we receive becomes a frozen portrait of how those objects looked eons ago, preserved in wavelength, timing, and intensity, offering scientists rare and precious clues to reconstruct early cosmic eras and to understand how galaxies, stars, and clusters formed when the universe was still young. Each photon carries the imprint of its birthplace, a snapshot encoded in energy, and together these ancient signals create timelines of events that would otherwise remain hidden forever. Yet even when stars shine brightly, not all of them can be seen, for dust-filled nebulae can hide fully formed stars behind thick veils of shadow, gathering in clusters so dense that visible light cannot pass through. These dark nebulae appear as silhouettes against glowing regions of space, concealing the vibrant activity within. Fine dust particles absorb and scatter short wavelengths, creating opaque curtains that hide newborn stars still gathering mass from surrounding clouds. But infrared observations reveal what the dust conceals, as longer wavelengths slip through more easily, allowing astronomers to see glowing protostars warming their surroundings, pulling in material through swirling disks that may eventually form planets. The same dust that obscures these stars also plays a vital role in their birth. It cools collapsing gas clouds, allowing gravity to continue pulling material inward until the young stars ignite. As the protostars grow stronger and begin shining with increasing intensity, their radiation pushes the surrounding fog outward, carving cavities, clearing lanes, and eventually revealing clusters that spent millions of years hidden in darkness, their first light finally reaching external observers. This interplay between shadow and hidden glow makes these nebulae essential laboratories for understanding stellar evolution, as they show how stars grow from faint, fragile beginnings into brilliant sources of light. But while dust protects young stars, it cannot shield vulnerable planets from the violence of stellar winds, for massive or highly active stars emit streams of charged particles at extreme speeds, sweeping outward through their planetary systems with forces strong enough to strip atmospheres from any world unable to defend itself. Planets orbiting too close may find their upper atmospheres battered constantly, the energy of incoming particles breaking molecules apart and heating atoms until they escape into space. Worlds lacking strong magnetic fields face the greatest danger, for without magnetic protection to divert the incoming wind, the atmosphere thins, leaving the surface exposed to harsh radiation, volatile temperature swings, and destructive ultraviolet light. Over time, a once temperate world with liquid water and clouds might lose its entire atmosphere, transforming into a barren sphere of exposed rock and frozen shadows. By studying these interactions, scientists determine which planets might remain stable for billions of years and which are destined for long-term depletion, shaping the search for life by revealing which environments remain safe against stellar aggression. Meanwhile, high-energy radiation from massive young stars sculpts the surrounding gas into towering pillars, grand structures formed when ultraviolet light sweeps outward and ionizes nearby material, pushing against it with pressure strong enough to erode vast regions of gas. Less dense areas evaporate first, while slightly denser clumps resist the blast, standing firm as the surrounding material is carved away. Over time, these resistant pockets stretch into elongated columns that point back toward the stars that sculpted them, forming spectacular cosmic monuments. Within the sheltered interiors of these pillars, gravity continues to work quietly, forming new protostars hidden from the harshest radiation. Observations of these structures reveal environments where destruction and creation take place simultaneously, where the intense light of young giants both shapes the clouds and triggers the birth of future generations of stars. Equally influential are the magnetic fields that twist and confine blazing streams of charged particles throughout galaxies, guiding their flow along invisible lines. These fields arise from the rotation of stars, the motion of ionized gas, and the dynamics of compact remnants like neutron stars, and when particles encounter them, their paths bend and spiral, tracing loops, arcs, or massive jets extending thousands of light-years into space. In regions with strong magnetic fields, charged particles may become trapped, bouncing back and forth or streaming along narrow pathways, creating structures that glow across multiple wavelengths. By studying these flows, astronomers can infer the strength and direction of magnetic fields that would otherwise remain invisible, gaining insight into how these forces shape energy distribution, influence star formation, and guide the evolution of cosmic structures across enormous scales. While magnetic fields shape the lives of stars and particles, planetary collisions shape the very architecture of worlds. In the chaotic youth of a planetary system, countless rocky bodies move along unstable paths, colliding frequently in violent encounters that reshape their surfaces, melt mountains, vaporize oceans, and sometimes merge two worlds into a single, larger planet. Other collisions tear planets apart entirely, scattering debris across the system, debris that may later form moons, rings, or smaller companion bodies. The heat generated by colossal impacts can create global magma oceans, resetting a planet's surface and erasing earlier geological histories. Cratered landscapes, tilted rotational axes, unusual planetary densities, and the composition of moons all preserve clues to these ancient catastrophes, and by studying them, researchers reconstruct the violent processes that shape the current arrangement of worlds. Each impact leaves a permanent record of events that occurred during the turbulent era of planetary formation. Far from the inner chaos of collisions, rings around distant planets reveal the subtle beauty of orbital dynamics, stretching wider than the distance between Earth and the Moon. These vast, intricate structures form when material becomes trapped in stable orbits rather than merging into moons. Dust, ice, and rocky fragments circle in countless individual paths, each responding to gravitational forces and tiny collisions with neighbors. The appearance of a ring system depends on the composition and size of its particles. Some shine brightly with fine icy grains that scatter starlight in shimmering bands, while others contain darker material that absorbs light and appears faint even when spanning enormous distances. In young systems, fresh debris from moon-forming collisions spreads into broad arcs that slowly evolve into complex patterns carved by gravitational interactions, forming narrow bands, waves, and gaps that shift over time. Observing ring systems reveals not only their present beauty but also the ancient stories of impacts, migrations, and orbital resonances that shape them. Together, these phenomena, from tidal heating in distant moons to the ancient journey of starlight, from hidden stars within dusty nebulae to atmospheric erosion by stellar winds, from towering pillars sculpted by ultraviolet radiation to magnetic fields guiding cosmic particles, from violent planetary collisions to the delicate architecture of planetary rings, paint a picture of a universe in ceaseless motion, governed by forces both gentle and overwhelming, where creation and destruction intertwine, and where every structure, every photon, every orbit, and every fragment of dust contributes to the vast, interconnected story of cosmic evolution. The changing distance causes shifts in gravitational pull that stretch and compress the moon repeatedly, and this continual flexing generates friction within the interior, warming layers of rock and ice that would otherwise remain frozen, gradually accumulating heat in a way that can melt deep pockets of material and form reservoirs of liquid far beneath the surface. While in some cases the heat drives plumes that erupt through cracks, releasing vapor and particles into space, and in others it fuels slow, swirling circulation within vast subsurface oceans hidden under thick crusts of ice, showing that these internal processes reshape landscapes from within and create environments where complex chemical reactions flourish despite the otherwise extreme cold of the surface, proving that tidal motion alone, without the need for sunlight, can transform the interior of a moon in ways that profoundly influence its geology and chemistry. Ancient starlight, meanwhile, crosses the cosmos for billions of years before reaching Earth, beginning its long journey from distant stars or galaxies that shine across the expanding universe, and as each beam travels it passes through regions filled with clusters, filaments, and voids that stretch, bend, or shift its color. Some wavelengths are absorbed by drifting gas clouds while others continue uninterrupted until they meet the mirrors of a telescope, and because the universe is vast and constantly expanding, the distance the photons travel is beyond comprehension, so by the time they arrive at Earth the sources that emitted them may have changed, evolved, or even vanished entirely, leaving the light behind as a frozen record of how those objects appeared eons ago, preserved within each photon's wavelength, intensity, and subtle distortions. Scientists decode these ancient signals to reconstruct the early eras of cosmic evolution, revealing structures as they looked when the universe itself was in its youth. And each photon becomes a messenger carrying memories of distant realms and times we could never witness directly, creating a timeline of cosmic events otherwise hidden forever. Dust-filled nebulae, in contrast, hide fully formed stars behind thick veils of shadow, where clouds of fine particles gather so densely that they block visible light, creating dark shapes that stand like silhouettes against glowing backgrounds and mask the stellar nurseries within. Yet infrared observations allow astronomers to peer into these concealed regions, revealing that many dark nebulae cradle young stars already glowing with heat as they grow by feeding on surrounding gas, forming disks that may later develop into planets. The dust that hides them also helps cool the cloud, enabling gravitational collapse to progress. And as these stars strengthen, their radiation slowly disperses the surrounding fog, revealing clusters that remained invisible for millions of years, demonstrating how the interplay between darkness and hidden light creates essential laboratories where astronomers observe stellar evolution from infancy to emergence. Violent stellar winds from massive or highly active stars can strip atmospheres away from vulnerable planets, as streams of charged particles sweep outward at tremendous speeds and collide with upper layers of planetary atmospheres, heating atoms until they leak into space. Planets without strong magnetic fields are especially vulnerable, lacking the protective shield needed to deflect incoming wind. And as the atmosphere thins, the surface becomes exposed to harsh radiation and severe temperature swings, which can dramatically transform a once habitable environment into a barren world. Studying such interactions helps scientists determine which planets may retain stable atmospheres and which are likely to lose them over long timescales, shaping the search for worlds that could support life. High-energy radiation from massive stars can sculpt nearby clouds into towering pillars by ionizing surrounding material and driving shock fronts that erode low-density regions while leaving denser areas intact, gradually forming elongated columns that point back toward the energetic sources that carved them. Within their sheltered interiors, gravity continues working to form new stars even as the outer layers are battered by ultraviolet light, creating regions where destruction and creation unfold simultaneously. These dramatic structures stand as monuments to the immense power of massive stars and the resilience of the raw material from which new stellar generations arise. In this dynamic universe, magnetic fields twist and confine blazing streams of charged particles across galaxies, shaping the paths of electrons and ions that spiral around invisible lines of force rather than moving freely. And in regions with strong magnetic fields, these particles become trapped and guided into narrow jets, arcs, or loops that glow across multiple wavelengths, revealing the underlying structure of cosmic magnetism. By studying the shapes and variations of these glowing threads, astronomers infer the strength, orientation, and behavior of magnetic fields that influence energy distribution, star formation, and the evolution of large-scale cosmic structures, phenomena that remain difficult to reproduce in laboratories on Earth. Planetary collisions, too, reshape entire worlds in single catastrophic moments, especially during the chaotic early stages of a system's formation when countless solid bodies travel along intersecting orbits. When two sizable objects collide at high speed, mountains can melt, oceans can vaporize, crusts can shatter. And sometimes the bodies merge into a larger world while at other times they tear each other apart and scatter fragments across space. Such debris may later form moons, rings, or smaller companion bodies, and the heat from such collisions can create global magma oceans that reset planetary surfaces. Evidence of ancient impacts is preserved in cratered surfaces, unusual rotations, and unexpected chemical compositions, allowing researchers to reconstruct violent histories that shaped planets in our solar system and beyond. Rings around distant planets, some stretching wider than the distance between Earth and the Moon, are formed when material becomes trapped in orbit rather than merging into a moon. Their brightness and texture depend on the size and composition of particles. Fine icy grains scatter light brilliantly while darker fragments absorb light and appear ghostly faint even when spanning vast distances. Young systems may develop fresh rings from collisions between forming moons, and over time gravitational interactions sculpt them into narrow bands, gaps, and waves that shift gradually as orbits evolve, revealing ancient impacts and the subtle forces shaping planetary systems. Some stars orbit each other so closely that they share outer layers of gas, forming extraordinary binary systems in which their gravitational fields overlap. As one star evolves into a swollen giant, its outer layers spill toward its companion, forming streams of flowing material that circulate under the competing pull of both stars. This mass transfer dramatically alters both stars. The receiving star grows hotter and brighter while the stripped star reveals inner layers normally hidden, and their shared atmosphere generates complex patterns of heat, motion, eruptions, and radiation pulses that vary in rhythmic cycles, providing astronomers with rare insight into stellar evolution influenced by companionship rather than solitude. Dense globular clusters, containing hundreds of thousands of stars packed closely into spherical shapes, orbit the outskirts of galaxies like ancient beacons of stellar history. Each cluster contains stars born at nearly the same time, making them some of the oldest surviving structures in the universe. And because the stars lie so close to one another, gravitational encounters occur frequently, flinging some stars outward, drawing others inward, and constantly reshaping internal motions. Some stars within these clusters become unusually bright and blue, likely formed through stellar mergers or mass transfer events triggered by close encounters. Despite constant movement, the clusters remain bound by their enormous combined mass, and studying them reveals insights into early star formation and how these ancient spheres have survived for billions of years. The interstellar medium carries shock waves from ancient supernova explosions, where a star's violent death sends powerful energy fronts sweeping through space, compressing gas and dust despite the medium's thinness. As these shock waves travel, they heat material, trigger new chemical reactions, excite atoms to glow, and continue expanding for millions of years, shaping clouds and sometimes influencing the birth of new stars. The resulting shells, bubbles, and filaments mark the paths of ancient explosions, and by studying their patterns, astronomers estimate the timing and energy of long-vanished stars. Some planets orbit their stars so rapidly that their years last only a few Earth days, moving along tight, swift paths that expose them to intense radiation and dramatic temperature extremes. Their star-facing sides can reach temperatures that melt rock, while their far sides may remain frigid unless powerful winds redistribute heat. Many are tidally locked, leaving one side in perpetual daylight and the other in endless night, creating atmospheric patterns struggling to keep up with rapid transitions. These extreme planets teach scientists how worlds behave under conditions far beyond anything found in our solar system. Spiral galaxies grow new arms when interacting with neighboring systems, as gravitational disturbances send waves of density across their disks, compressing material into arcs that gradually curve into spiral arms. These arms are patterns rather than fixed structures, and as gas becomes denser within them, new stars form and enhance the spiral shape. Repeated interactions over millions of years reshape entire galaxies, sometimes adding new arms while twisting older ones into distorted forms, illustrating how galactic evolution is guided by gravitational encounters. Massive star clusters illuminate surrounding gas clouds with intense ultraviolet radiation, ionizing hydrogen-rich regions, stripping electrons, heating gas, and causing glowing nebulae full of sculpted tendrils, pillars, and ridges formed by radiation and stellar winds. Over time, the brightest stars burn out quickly, changing the balance of light and shadow, and these illuminated regions reveal how star formation progresses and how young stars influence their environments. Rogue stars, flung from their home galaxies by gravitational interactions or supermassive black holes, travel through intergalactic space at immense speeds, carrying chemical signatures of their origins through regions where matter is sparse and starlight is faint, and by tracking their trajectories, astronomers uncover the violent events that expelled them. Some planetary systems form multiple asteroid belts resembling cosmic rings, where leftover material remains in stable orbits. Gravitational interactions shape these belts into separated regions, with gaps formed by resonances that clear paths through the debris. And studying these structures helps astronomers compare distant systems to our own asteroid belt and Kuiper region. Quasars shine with the power of trillions of stars, fueled by supermassive black holes pulling gas inward. The material heats to extreme temperatures in an accretion disk, radiating enormous luminosity across all wavelengths. while surrounding clouds absorb and re-emit this radiation in distinctive spectral patterns. Quasars were far more common in the early universe when galaxies were rapidly feeding their central black holes, and their immense brightness allows them to be observed across extraordinary distances. Astrobiologists. When starlight passes through a planet's atmosphere during its orbit around a star, that light becomes subtly transformed by every molecule, particle, and complex mixture it encounters, imprinting faint chemical signatures upon the spectrum that sensitive scientific instruments can later separate into individual wavelengths, revealing the presence of substances that might indicate biological activity or exotic environmental conditions unique to that world. Molecules such as oxygen, methane, ozone, and other reactive gases are of particular interest because they tend to break down or vanish quickly unless something continuously replenishes them, and on Earth, for example, the balance of these gases is maintained by the constant activity of living organisms interacting with sunlight, water, soil, and countless biological and geological cycles that keep the atmosphere stable over long periods. Astrobiologists therefore combine detailed atmospheric models, laboratory experiments, simulations of exotic planetary environments, and observations gathered from multiple wavelengths to determine whether unusual chemical mixtures could arise purely from natural non-biological processes, such as volcanic eruptions, photochemical reactions, or surface-atmosphere interactions, or whether the patterns they observe might require something more dynamic, potentially hinting at biological activity. Unlike anything we have encountered before, their work requires extreme caution, patience, and broad scientific insight because planets, particularly those unlike Earth, can produce surprising and complex chemistry in the absence of life, making it essential to rule out every abiotic explanation before considering more extraordinary possibilities. Even so, each new atmosphere that scientists analyze contributes to a steadily expanding library of planetary behaviors, environmental patterns, and chemical combinations, and this growing catalog helps refine our search for planets capable of hosting stable climates, long-lasting environmental cycles, liquid surface or subsurface water, and energy sources that could support biology in forms either familiar to our experience or entirely alien. While some planets reveal clues through their atmospheres, the surfaces of certain moons elsewhere in the solar system and beyond are constantly reshaped by dramatic cryovolcanic eruptions, driven not by molten rock as on Earth but by reservoirs of liquid water, ammonia, nitrogen, methane, or other volatile compounds kept warm beneath thick icy crusts by internal heating, tidal forces, and chemical reactions. These hidden subsurface oceans churn, shift, and pressurize the materials within them until fractures or weak points in the ice open, allowing plumes of pressurized liquid or vapor to escape into space in towering geysers or spread across the surface in flows that freeze into smooth plains, ridges, mottled textures, and complex structures that renew the landscape over time. This resurfacing can erase impact craters, hide geological history, and create worlds that appear young despite being billions of years old. By observing these ever-changing terrains and studying the chemistry within their plumes, scientists learn how internal heat, powerful gravitational interactions, and intricate chemical networks can sustain activity on worlds far from the warmth of their stars. And the existence of liquid environments beneath the surface raises profound and exciting questions about what forms of chemistry or even life might persist within these protected, energy-rich habitats. While icy moons reshape themselves from within, the universe also reveals extraordinary behavior on much larger scales, such as gravitational lensing, where massive objects like galaxy clusters bend the path of light traveling from even more distant galaxies. As photons journey across cosmic space, they move through regions warped by the distribution of mass, and when a massive object lies along the line of sight between Earth and something far beyond, the curvature of space around that object alters the path the light follows. This bending stretches, brightens, or multiplies the appearance of the distant galaxy so that instead of a faint smudge, observers may see extended arcs, elegant rings, or multiple mirrored images, all tracing the gravitational distortion of space. Such magnification allows astronomers to study structures that formed when the universe was young, revealing star formation rates, dust content, elemental composition, and the assembly processes of early galaxies. By analyzing how the light is warped, researchers can also map the distribution of mass within the lensing object, including elusive dark matter that emits no light yet strongly influences gravity. Every gravitational lens becomes a natural cosmic telescope constructed by the universe itself, offering a rare opportunity to observe regions far too distant for direct study with ordinary instruments. In closer stellar environments, young stars often flicker unpredictably as dust clouds drift across the line of sight. Within stellar nurseries where stars begin their lives, gas and dust remain abundant, and young stars frequently possess swirling disks of leftover material that will eventually give rise to planets, moons, and smaller bodies. Clumps and waves within these disks can momentarily block or dim the starlight, creating fluctuations that often follow no clear pattern because the dust distribution shifts constantly under the influence of stellar winds, radiation pressure, magnetic fields, and the gravitational pull of forming planets. Some stars dim slowly and brighten suddenly, while others follow chaotic, irregular rhythms. These variations offer valuable clues about the structure, density, and movement within the disks, enabling scientists to detect rings, gaps, warps, spirals, and regions where material accumulates. Such observations also reveal where nascent planets might be forming, as their gravitational influence sculpts the dust into distinctive patterns. The flickering of young stars thus becomes a window into the earliest, most dynamic stages of planetary system evolution, capturing the chaotic processes through which new solar systems take shape. On galactic scales, some galaxies grow steadily by consuming smaller companions, as galaxies rarely evolve in isolation. In crowded cosmic regions, large galaxies often encounter smaller ones, and gravity gradually pulls them together. As the smaller galaxy spirals inward over millions or billions of years, it loses stars and gas that stretch behind it in luminous tidal streams marking the path of the cosmic merger. Colliding gas clouds can compress, triggering bursts of intense star formation, while the stars from the smaller galaxy eventually merge into the halo, or inner regions of the larger one. These absorbed stars often carry chemical signatures distinct from the galaxy that consumed them, allowing astronomers to reconstruct the history of past mergers and understand how galaxies acquire their shapes, halos, and layered structures. Over cosmic time, each consumed companion becomes part of a larger whole, its identity preserved only in faint trails and subtle imprints. Within individual planetary systems, some exoplanets glow faintly as their atmospheres heat up under intense starlight, especially when a planet orbits extremely close to its star. High levels of radiation warm the atmosphere to temperatures far beyond those found on Earth, causing excited atoms and molecules to emit energy as a delicate glow visible in infrared, or even visible wavelengths. These emissions reveal the composition, temperature, and movement of gases, and in some planets, winds carry heat from the scorching day side to the cooler night side, shifting the pattern of the glow across the surface. Certain compounds form or break apart under ultraviolet radiation, adding extra brightness or altering the planet's spectral fingerprint. By observing these faint emissions at different points in the planet's orbit, scientists can reconstruct weather patterns, thermal gradients, atmospheric circulation, and even storm activity on worlds that appear only as single points of light. On stellar scales, the luminous structures known as planetary nebulae form when medium-sized stars near the end of their lives shed their outer layers through slow winds and gentle pulsations. As those drifting layers expand, the hot exposed core emits ultraviolet light that makes the gas glow in vivid colors reflecting its composition and density. The shapes that emerge, rings, glowing ovals, hourglass forms, spirals, and intricate filaments, depend on factors such as stellar rotation, magnetic fields, or interactions with companion stars. Over thousands of years, the nebula expands and thins until it fades into interstellar space, leaving behind a compact remnant that cools slowly over billions of years. These nebulae reveal how stars recycle elements such as carbon, nitrogen, oxygen, and heavier materials back into the galaxy, enriching future generations of stars and planets. At the centers of many galaxies, supermassive black holes regulate the formation of stars across vast regions. These enormous black holes gather in falling material into swirling accretion disks, and when large amounts of gas fall inward, the environment near the core becomes extraordinarily energetic. Jets, winds, and radiation blast outward, heating surrounding gas and in some cases preventing new stars from forming, while in other situations, these energetic outflows compress clouds and trigger bursts of star birth. The feedback from supermassive black holes shapes galaxies on scales spanning tens or even hundreds of thousands of light years, influencing their evolution, structure, and long-term behavior. Across all these phenomena, from atmospheric fingerprints carried in starlight, to icy moons erupting into space, to galaxies bending light through gravity, to young stars flickering through dust, to planets glowing under searing heat, to nebulae marking the gentle end of stellar lives, to black holes governing galactic ecosystems, the universe reveals itself as a place of endless complexity, constant renewal, and ever-deepening mystery. When starlight passes through a planet's atmosphere during its orbit, it carries faint imprints created by the molecules it encounters, and these subtle signatures become a treasure trove of information for astronomers who use sensitive instruments to separate the light into its component colors and reveal gases that may hint at biological activity, such as oxygen, methane, and other reactive substances that should quickly disappear unless something continuously replenishes them, just as living organisms do on Earth through constant interaction with air, water, and sunlight. So astrobiologists combine atmospheric models, laboratory simulations, and observations across many wavelengths to determine whether unusual chemical mixtures could arise from geological or photochemical processes alone or if they might require something more dynamic, such as microbial life. Though they proceed with great caution because planets can surprise us with exotic chemistry produced without biology, yet each newly studied atmosphere adds to a growing library that helps refine the search for planets with stable climates, liquid water, and complex cycles capable of supporting familiar or entirely alien forms of life. Meanwhile, the surfaces of certain icy moons across the outer solar system are constantly reshaped by cryovolcanic eruptions driven by interior heat that keeps subsurface mixtures of water, ammonia, nitrogen, or other volatiles in liquid form beneath their frozen crusts, and pressure builds as these hidden oceans slowly churn until cracks open in the ice and release jets of material that shoot into space or spread across the landscape, gradually smoothing terrain, forming ridges, and erasing ancient impact craters, thereby hiding the geological history that might otherwise remain visible. But studying these ever-changing surfaces helps scientists understand how internal heat, tidal forces from giant planets, and complex chemistry maintain activity in distant, cold worlds, raising profound questions about what environments might exist in these protected energy-rich habitats and whether life could emerge far from starlight. In the vastness of the universe, gravitational lensing serves as a natural telescope where massive objects curve the fabric of space and bend passing light, magnifying distant galaxies that would otherwise be invisible, stretching or duplicating them into arcs or rings that reveal structures formed when the universe was young, offering insight into early star formation, dust, and galactic evolution, while the amount and shape of distortion allow researchers to map the mass of the lensing object, including dark matter that emits no light, turning each lensing event into a cosmic magnifying glass carefully crafted by gravity itself. In stellar nurseries, young stars flicker unpredictably as clouds of dust drift across the line of sight. For these stars are surrounded by swirling disks of leftover material that will eventually form planets, moons, and smaller bodies, and the dust within these disks shifts under the influence of winds, magnetic fields, and gravity, creating irregular patterns of brightening and dimming that help astronomers map the structure of the disks, detect gaps and warps, and identify regions where planets may be forming, offering a glimpse into the earliest stages of solar system development across the cosmos. Some galaxies grow by consuming smaller companions, pulling them inward over millions of years, stripping away their gas and stars and leaving luminous tidal streams that trace the path of the merging process, triggering bursts of star formation as clouds collide and compress, while the absorbed stars, with their distinct chemical fingerprints, become part of the larger galaxy's halo and inner regions, preserving a faint record of long-ago mergers that shaped its structure. On planets orbiting close to their stars, atmospheres glow faintly as intense radiation heats their gases to extraordinary temperatures, causing molecules to emit light detectable at infrared or visible wavelengths. And this glow shifts across the surface as fierce winds redistribute heat between day and night, while ultraviolet radiation triggers reactions that create additional brightness. So by observing these emissions during different phases of the orbit, scientists reconstruct atmospheric dynamics and weather patterns on worlds visible only as single points of light. When stars, similar to our Sun near the ends of their lives, they shed their outer layers and form planetary nebulae, glowing shells of gas illuminated by the hot stellar core, shaped into rings, ovals, or delicate patterns by rotation, magnetic fields, or interactions with companion stars, expanding over thousands of years until they fade into interstellar space while the core becomes a white dwarf that will cool slowly for billions of years, and these nebulae recycle material back into the galaxy, enriching future stars and planets with heavy elements. In many galaxies, supermassive black holes regulate star formation by releasing powerful winds, jets, and radiation when they consume large amounts of material, heating the surrounding gas and pushing it away so it cannot collapse into new stars, creating a delicate balance between feeding the black hole and allowing the galaxy to grow. Explaining why galaxies with active centers often show reduced star formation while those with quiet centers continue forming stars steadily, revealing the interconnected evolution of black holes and galaxies. Within our own galaxy, some stars travel on paths tilted far above or below the Milky Way's disk, tracing orbits shaped by ancient mergers or gravitational disturbances, offering a three-dimensional map of the galaxy's structure and mass distribution, including the unseen contribution of dark matter. While chemical analysis shows that some of these stars originated in dwarf galaxies long ago absorbed by the Milky Way, preserving clues to its dynamic history, shock waves from supernova explosions can trigger new star formation by compressing nearby molecular clouds until gravity causes them to collapse, demonstrating how the death of one star can ignite the birth of many others, renewing galactic regions and driving the cycle of stellar generations. In extremely close binary star systems, one star may expand until its outer layers overflow and drift toward its companion, forming a streaming bridge of gas that can gather into a swirling accretion disk around the receiving star, dramatically altering both objects by stripping one and increasing the mass and brightness of the other, sometimes producing sudden outbursts when accumulated gas heats rapidly or undergoes explosive reactions, showing how close companionship reshapes stellar evolution in ways solitary stars never experience. Cosmic dust grains formed in the cool outer layers of dying stars contain crystalline structures with unique chemical fingerprints, scattered across the galaxy by stellar winds and supernovae, becoming part of the material that forms new stars and planets. And some grains older than the solar system itself reveal the deep history of cosmic recycling. In dense stellar nurseries, gravity gathers gas and dust into long, thread-like filaments that wind through space like illuminated strands, channeling material into knots that collapse into newborn stars surrounded by swirling disks. While magnetic fields and turbulence twist the filaments into evolving shapes visible at multiple wavelengths, creating entire clusters rather than isolated stars and showing how the galaxy renews itself through interconnected processes. Some planets grow massive hydrogen atmospheres that dwarf their rocky cores by capturing light gases early in their formation, creating deep, extreme environments where pressures and temperatures soar and winds sweep across the entire planet, while the chemical properties of these thick atmospheres preserve clues to the planet's history and growth. By studying the chemical fingerprints imprinted on starlight as it filters through such atmospheres during transits, scientists detect gases that reveal climate, weather, and geological activity on planets that cannot be directly imaged, using only the light they transmit to explore worlds across the galaxy, making this one of the most powerful tools for studying distant atmospheres without sending spacecraft. Finally, relics of ancient galaxies remain scattered throughout the Milky Way as thin stellar streams, faint ribbons of light formed from the remnants of smaller galaxies torn apart by our own over billions of years, each one carrying chemical signatures different from stars born in the Milky Way, allowing astronomers to reconstruct past merger events and understand how the galaxy slowly assembled its present form through countless interactions, collisions, and absorptions that shaped the structure we see today. Some relics of long-vanished galaxies appear as faint clusters still holding together, while others have dispersed into the broader halo of the Milky Way, and together they form a historical record preserved in starlight, revealing how our galaxy grew over billions of years by gradually absorbing smaller neighbors and incorporating their stars, gas, and dust into its structure. A process that leaves subtle chemical and dynamical traces for astronomers to decode, and within this broader context, many individual stars are surrounded by dusty disks left over from planet formation, whereafter planets coalesce from swirling disks of gas and debris. Leftover material continues to orbit the central star in belts of fragments ranging from microscopic dust grains to kilometer-scale objects, and through continual collisions, these fragments grind down into fine dust that spreads across the system, absorbing starlight and re-emitting it at longer wavelengths to create a thermal signature. Detectable with specialized telescopes, the structure of these circumstellar disks is strongly influenced by the presence of planets, which can carve gaps, shepherd rings, and scatter material into new configurations, revealing the system's architecture and identifying regions where additional planets might still be forming, and while radiation pressure and collisional processes gradually remove dust over time. Some disks persist for hundreds of millions of years, effectively acting as archives of early planetary history, preserving clues about the dynamics and composition of the primordial nebula from which the planetary system arose. On a much larger scale, intergalactic gas stretches in narrow filaments that weave between distant clusters, forming part of the cosmic web, a vast, interconnected network of clusters, nodes, and strands of matter where diffuse gas enriched with elements from previous generations of stars channels material into growing galaxies, guiding their motions, influencing cluster evolution, and shaping the distribution of mass on the larger scales. And though these filaments are faint and tenuous, their existence confirms theoretical predictions about cosmic evolution, illustrating how the universe organizes itself into a structured hierarchy, delivering the raw material necessary for new stars to form and for galaxies to continue expanding their stellar populations. Intertwined with these large-scale structures, cosmic magnetic fields play a subtle but critical role, arising from the motion of conductive plasma within stars, galaxies, and intergalactic gas, forming invisible pathways that guide the motion of charged particles across immense distances, forcing electrons and ions to spiral along magnetic lines while emitting detectable radiation. And these fields vary in strength and orientation, influencing the behavior of cosmic rays, shaping the structure of nebulae and jets, trapping particles in loops, and channeling them into narrow beams that stretch far from their points of origin, thereby contributing to the overall dynamics of the universe, demonstrating that unseen forces can profoundly affect the flow of energy alongside gravity and pressure. Some planetary systems orbit dead stars that emit little more than faint ghostly light, where moderate-mass stars, after exhausting their fuel, shed their outer layers and leave behind compact remnants that slowly cool over time and produce only a dim glow. Yet despite the dramatic transformations of their parent stars, some planets survive, enduring extreme environmental changes. From intense heating during the star's final active phases to prolonged deep freezes once the stellar remnant fades. And while some surviving planets may experience strong tidal forces due to proximity, others drift in frigid outer orbits, revealing that planetary bodies can persist even when their stars cease to shine brightly. And studying these systems provides insight into how planets endure evolving stellar conditions. Within some of these worlds, gas giant planets emit faint infrared radiation as internal heat escapes through thick atmospheres dominated by hydrogen and helium, with this energy absorbed and re-emitted by atmospheric gases to produce a gentle glow detectable by specialized instruments, revealing temperatures, circulation patterns, and chemical composition. While powerful winds redistribute heat across vast planetary surfaces and storms stir warm material from the interior, producing local brightening that betrays the underlying dynamics of these massive atmospheres, offering a window into weather systems and energy transport on a scale far beyond anything observed on Earth. Similarly, tidal interactions in close binary star systems can elongate stellar envelopes, where mutual gravitational forces pull unevenly across a star's surface, stretching its outer layers along the line connecting the two stars, creating subtle variations in shape and brightness that shift as the stars orbit one another, influencing stellar rotation, internal energy transport, mass loss, and in some cases the transfer of material from one star to another, illustrating how gravity sculpts stars just as effectively as it shapes planets and galaxies. On the scale of entire galaxies, enormous cavities sometimes appear where past energetic events have cleared out vast regions of gas, forming hollowed-out spaces thought to result from the collective effects of supernova explosions, powerful outflows from central black holes, or intense bursts of star formation, where expanding shock waves sweep away gas and dust to leave bubbles that persist long after the events that created them, and the size, shape, and distribution of these cavities serve as a historical record of energy injection into the galactic environment, influencing the future rate and location of star formation, regulating the availability of gas, and illustrating the dynamic interplay between energetic feedback and galactic evolution. Even in the coldest reaches of space, interstellar clouds demonstrate remarkable chemistry, as low temperatures allow gas molecules to freeze onto dust grains, forming thin icy mantles composed of water, carbon dioxide, methane, and other compounds, which accumulate layer by layer over long periods. And cosmic rays or faint ultraviolet photons trigger slow reactions within these ices to create more complex molecules that enrich the cloud with ingredients that may later participate in star and planet formation. And when such a cloud collapses, heat from nascent stars evaporates the ice, releasing a chemically diverse mixture into the surrounding gas, contributing to the material from which subsequent generations of stars and planetary systems emerge. These processes, from the survival of planetary remnants around dead stars to the formation of complex molecules in icy interstellar clouds, from the shaping of binary stars by tidal forces to the infrared glow of gas giants, from dusty circumstellar disks to filaments of intergalactic gas, together weave an intricate narrative of cosmic evolution, revealing the interconnected nature of physical forces, chemical processes, and stellar and planetary life cycles, where every event leaves subtle but measurable imprints that astronomers can decode to reconstruct the history of galaxies, star clusters, planetary systems, and the intergalactic medium, showing how the universe constantly recycles material, redistributes energy, and shapes structures across an enormous range of scales, and within this vast continuum, stars, planets, gas, dust, magnetic fields, and dark matter interact in ways that define the form and function of cosmic structures, provide energy for emergent systems, and deliver the ingredients for planetary formation, potentially including the chemistry necessary for life. While the long-lived relics of accreted galaxies, the frozen mantles of interstellar dust, and the subtle glow of planetary atmospheres all serve as tangible records of these processes, allowing us to piece together the story of our galaxy's assembly, the evolution of stars and planets, and the ongoing cycle of destruction and creation that permeates the universe, where the death of one system provides the raw material for the next, where energy released in one region shapes distant formations, and where even the faintest objects, whether planetary remnants, dust grains, or gas filaments, participate in a larger cosmic tapestry, each contributing to the structure, chemistry, and dynamics that define the observable universe, illustrating how matter, energy, and forces interact across time and space to build the galaxies, stars, and planetary systems we study today, providing insight into the processes that govern formation, evolution, and survival in environments ranging from the coldest interstellar clouds to the hottest stellar cores. And by examining these relics, dust disks, gas filaments, magnetic fields, cavities, and glowing atmospheres, astronomers continue to deepen their understanding of cosmic history, the life cycle of matter, and the fundamental physical laws that orchestrate the universe, revealing a grand narrative in which every particle, photon, and molecule plays a part in shaping the ever-changing universe we inhabit. These icy grains act as tiny storage sites preserving the earliest stages of chemical evolution in the galaxy, locking within them the raw ingredients from which stars, planets, and potentially life itself can emerge. Stellar mass black holes form when massive stars, many times larger than the Sun, exhaust their fuel and collapse under the relentless pull of gravity, As nuclear fusion in the core can no longer counteract the star's weight, the core implodes, compressing matter to extraordinary densities, and if nothing halts this contraction, a black hole emerges. A compact object with the mass of the original star squeezed into a volume of unimaginable smallness, while the outer layers explode outward in a supernova, scattering heavy elements across surrounding space. Though black holes emit no light themselves, their presence is revealed through interactions with surrounding matter, as gas and dust spiral inward, heat up, and emit detectable radiation, demonstrating how the death of a single massive star can produce one of the most extreme and fascinating objects in the universe. Neutron stars, formed when some stars explode and leave behind cores composed almost entirely of densely packed neutrons, provide a laboratory for studying matter under conditions impossible to replicate on Earth. Their surfaces appear solid yet consist of neutron-rich crusts where electrons have merged with protons, and deeper layers reach densities so extreme that their physical properties remain an active subject of research. The gravity at a neutron star's surface is so immense that even a minor irregularity can weigh millions of tons, and as these stars rotate or shift, stresses accumulate until sudden adjustments release bursts of radiation that astronomers detect as fleeting flashes, offering rare insights into the behavior of matter under incomprehensible pressures. In planetary systems, some exoplanets orbit within chaotic environments where the gravitational influence of multiple neighboring planets produces constantly shifting orbits. Subtle tugs accumulate over time, gradually altering orbital shapes and inclinations, sometimes causing planets to drift inward or outward, or even ejecting them from the system entirely, demonstrating that planetary arrangements can be dynamic and unpredictable, and far from the orderly configuration seen in our solar system. Young stars often launch powerful jets that carve long channels through the surrounding gas, where magnetic fields guide infalling material toward the poles, creating narrow, high-speed outflows that compress and heat the gas they encounter, forming glowing knots and elongated cavities. As the jets move and the young star rotates, ripples and structures emerge along these channels, revealing how early stellar growth transfers angular momentum and sculpts the birth environment, while providing a visible record of the interplay between nascent stars and their natal clouds. On a galactic scale, ultra-faint dwarf galaxies contain relatively few stars but are dominated by dark matter, with stellar motions indicating far more mass than visible matter can account for, demonstrating the stabilizing role of dark matter in maintaining their structure and offering valuable insight into the distribution and behavior of dark matter on small scales. These dwarf galaxies preserve ancient stellar populations formed long before the Milky Way assumed its current shape, providing glimpses of early cosmic conditions and the processes that govern the assembly of larger galaxies. Star formation can stall when the intense radiation from massive stars heats and disperses surrounding gas, breaking apart molecules and preventing gravitational collapse, with the effect extending across entire star-forming regions and regulating where new stars can emerge, illustrating the delicate balance between heating and cooling that controls the pace of stellar birth across galaxies. On certain frigid exoplanets far from their stars, seas of liquid hydrocarbons replace water, as methane and ethane condense into lakes and rivers under extremely low temperatures, flowing across basins sculpted over millions of years, forming coastlines and channels shaped by exotic precipitation cycles, while hydrocarbon clouds in the atmosphere create repeating storms and replenish these bodies of liquid, demonstrating that even under conditions vastly different from Earth, planets can host active climates and complex chemistry. Gamma ray bursts represent some of the most energetic events in the cosmos, occurring when massive stars collapse into compact remnants or when dense stellar corpses merge, releasing concentrated flashes of high-energy radiation that can briefly outshine entire galaxies along narrow jets. And if such a jet aligns with Earth, astronomers detect a brilliant flare lasting from fractions of a second to several minutes, with afterglows continuing as the shock wave interacts with surrounding material, providing critical insight into extreme magnetic fields, rapid particle acceleration, and the dispersal of heavy elements across galaxies. Asteroid families, remnants of ancient collisions in the early solar system, retain common compositions and trajectories that reveal the history of their parent bodies, with gravitational interactions continuing to modify orbits over billions of years, helping researchers trace the timing and impact of early collisions that influenced the distribution of material from which moons, planets, and comets eventually formed. Planetary magnetic fields trap charged particles, guiding them along invisible lines into giant belts that glow as particles spiral, a process fueled by solar wind and cosmic rays, which illuminates interactions between magnetic fields and charged matter. These processes, alongside the formation of black holes, neutron stars, chaotic planetary orbits, stellar jets, dwarf galaxies, stalled star formation, hydrocarbon seas, gamma-ray bursts, asteroid families, and magnetically trapped particles, collectively paint a picture of a universe that is dynamic, interconnected, and constantly evolving, where matter cycles between stars and planets. Energy propagates across scales from the infinitesimal to the galactic, and the laws of physics orchestrate complex phenomena from the behavior of subatomic particles to the motion of entire galaxies. Within this grand framework, the remnants of ancient events, whether icy grains in molecular clouds, faint dwarf galaxies, or dust disks around stars, act as tangible records of cosmic history, preserving the chemical, structural, and dynamical fingerprints of processes that have shaped the universe over billions of years. The interplay between gravity, radiation, magnetic fields, and the intrinsic properties of matter-governed star and planet formation dictates the evolution of stellar remnants and regulates the flow of energy through interstellar and intergalactic space, while observations across multiple wavelengths, from infrared emissions of gas giants to high-energy radiation from gamma-ray bursts, allows scientists to reconstruct these processes and understand their consequences. Across scales ranging from sub-millimeter dust grains to entire galactic filaments, the universe demonstrates an extraordinary capacity for recycling matter and energy. Supernovae distribute heavy elements, black holes and neutron stars mark endpoints of stellar evolution, dwarf galaxies preserve relic populations and dark matter, and planetary systems reveal the diversity and dynamism of orbital mechanics, atmospheres, and surface chemistry. Through careful observation, analysis, and modeling, astronomers continue to uncover the complex interconnections between these phenomena, elucidating how energy and matter flow through cosmic systems, how extreme environments test the limits of physics, and how seemingly isolated events contribute to the ongoing evolution of stars, planets, and galaxies. Revealing a cosmos in which destruction is inseparable from creation, where each stage of a system's life sets the conditions for the next, and where even the faintest objects, icy grains, dust belts, or ultra-faint galaxies, play a critical role in the continuous unfolding of universal processes that define the structure, composition, and dynamics of everything we observe. As charged particles spiral along a planet's magnetic field lines, they collide with atmospheric molecules or interact with the field itself, releasing energy in the form of faint light that encircles the planet in broad, toroidal belts, which can shift and brighten when bursts of stellar activity inject additional particles into the system, revealing intricate details about the strength and shape of the magnetic field and demonstrating how such fields influence planetary habitability by shielding worlds from harmful radiation. These glowing regions exemplify how unseen forces create dynamic structures that govern long-term planetary evolution and interact with the environment on multiple scales. Near black holes, relativistic effects distort the passage of time, stretching the fabric of spacetime such that an object falling toward the event horizon appears to slow and freeze when viewed by a distant observer, while for the object itself, time continues normally, illustrating that gravity shapes both spatial trajectories and the progression of time itself, with the distortions intensifying closer to the black hole and observable through shifts in signals from infalling matter, offering essential insight into how these extreme objects interact with their surroundings and demonstrating that time is not a fixed background but a malleable quantity influenced by mass and motion. On larger scales, galaxies rotate around invisible halos of dark matter, whose gravitational influence dominates the motion of stars, gas, and dust, holding the galaxy together despite rotation speeds too high to be explained by luminous matter alone. Stars orbit within these halos following paths dictated by the unseen mass, and mapping these motions through rotation curves allows astronomers to infer the structure, density, and distribution of dark matter, revealing crucial information about The composition of the universe and the mechanisms governing cosmic evolution. Exoplanets can possess exotic atmospheres where extreme temperatures near their parent stars vaporize solid minerals, lifting them into the upper atmosphere where they condense into clouds of droplets or crystals. Winds transport these mineral-rich vapors across the sky, producing brightness variations that shift with rotation and orbital phase, offering scientists the ability to model day-night temperature gradients and atmospheric chemistry, while illustrating the extraordinary diversity of planetary atmospheres and how familiar elements behave unpredictably under conditions far removed from those on Earth. Neutron stars, the dense remnants of certain stellar explosions, have crusts that behave like rigid surfaces atop matter packed at extraordinary densities, and as they rotate or undergo internal changes, stresses accumulate until sudden shifts, star quakes, release bursts of high-energy radiation detectable across vast distances, sometimes subtly altering the rotation of the star itself and providing unique insights into matter under conditions unattainable on Earth, showing how compact objects respond dynamically to internal and external forces. Some stars are so massive that they fuse elements up to iron in their cores, progressing rapidly through hydrogen, helium, carbon, oxygen, neon, and silicon, ultimately producing iron, at which point energy production ceases, the outward pressure fails, and the core collapses, triggering a catastrophic supernova explosion that distributes heavy elements into the surrounding interstellar medium, enriching the galaxy with the raw materials for future stars and planetary systems, illustrating the vital role of massive stars in shaping cosmic environments and sustaining the chemical evolution necessary for life. Far beyond giant planets, icy bodies orbit in the cold outer reaches of planetary systems where temperatures are low enough for volatile compounds such as water, methane, and carbon dioxide to freeze, preserving these objects for billions of years. They remain largely unaltered, serving as time capsules that record the conditions of early planetary formation, and by studying their orbits and distribution, scientists can infer the history of planetary migration, the development of protoplanetary disks, and the prevalence of distant reservoirs of material that may later seed comets, moons, or other small icy bodies. Between galaxies, the faint glow of ancient stars persists in the intergalactic medium, remnants of stellar activity from long-dead systems, so subtle that it requires sensitive instrumentation to detect, yet it carries information about the cumulative light of countless generations of stars, offering a glimpse into the history of cosmic illumination and the recycling of matter on scales that span millions of light-years. These processes, from planetary magnetic belts and exotic atmospheric clouds to relativistic time dilation, dark matter halos, neutron star quakes, massive stellar evolution, outer icy reservoirs, and the faint afterglow of ancient galaxies, illustrate the intricate interplay of forces that govern the cosmos, demonstrating that even the faintest or most extreme phenomena contribute to a continuous cycle of energy and matter, where creation and destruction are inseparable, and where observing the universe across multiple scales, from subatomic particles to galaxy clusters, reveals a tapestry of interconnections that define the structure, composition, and dynamics of everything we see. Through detailed observations and careful modeling, astronomers trace the flow of energy and matter, understand the role of hidden forces, and uncover the mechanisms by which stars, planets, and galaxies evolve over billions of years, showing that the universe is not static but an ever-changing, complex system in which each process, from the microcosmic interactions of charged particles to the grand motions of galaxies, is a part of a continuous chain of cause and effect, reflecting a cosmos in which extremes coexist with subtlety, and where light, matter, and gravity combine to produce the astonishing variety of structures that populate the observable universe, highlighting the interplay between visible and invisible forces, and revealing the ongoing narrative of cosmic evolution in which even the most ephemeral phenomena, tiny icy grains, mineral clouds, star quakes, and faint intergalactic light, play an essential role in shaping the universe we inhabit. The faint intergalactic glow arises from stars that were stripped from their original galaxies during past collisions and gravitational interactions, flung into intergalactic space as galaxies passed one another or merged, continuing to shine in isolation, and over time, many of these stars dimmed, aged, and eventually faded. Yet their collective light creates a soft radiance that fills the darkness between galaxy clusters, serving as a quiet record of cosmic history that reveals the long and intricate journeys of stars far from any galaxy. And by analyzing this emission, astronomers can reconstruct events spanning billions of years, deducing how often galaxies collided, merged, or cannibalized their neighbors. In the solar system, comets exemplify the interplay of heat and volatile materials as they release jets of dust and gas when approaching their stars. These icy wanderers, having spent most of their existence in frigid outer regions, begin to vaporize when sunlight penetrates their outer layers, generating pressure that bursts outward through cracks in the crust, carrying dust, gas, and ice into space to form bright comas and elongated tails that point away from the star, while the jet's rotation, pulsing, and shifting behavior reflects the comet's spin and surface properties, providing insight into the composition and internal structure of these ancient objects, revealing volatile compounds preserved since the solar system's birth that return briefly to visibility before fading into the cold. On galactic scales, powerful winds generated by massive stars and their explosions can expel gas from galaxies, quenching star formation by pushing surrounding material outward with tremendous force, creating cavities and channels in the galactic medium, reducing the supply of dense gas required to form new stars, and regulating the long-term evolution of galaxies by balancing the cycle of creation and destruction, showing that feedback from stars plays a central role in shaping the growth, structure, and activity of galaxies. Stars themselves can be accelerated to high velocities after gravitational encounters with clusters, binary companions, or spiral arms, sometimes gaining sufficient speed to escape the galaxy entirely or, at lower velocities, to travel far from their birthplaces. And by tracing these wandering stars' paths, astronomers gain insights into the dynamic gravitational landscape of the Milky Way, where each fast-moving star becomes a messenger of past interactions and forces. On some exoplanets, surfaces can be transformed into oceans of molten rock due to extreme proximity to their stars, with high temperatures melting the crust to form seas of liquid rock that glow with intense heat, while vaporized minerals form dynamic atmospheres that condense into glowing clouds, transported by winds to cooler regions where they solidify as mineral-rich rain. With the boundary between molten and solid terrain shifting continually, creating dramatic contrasts between scorching day sides and cooler night sides. Observing the light emitted by such planets allows scientists to infer the composition and temperature of molten surfaces, revealing how stellar proximity can radically transform planetary geology. Supernova remnants provide additional insights into cosmic recycling, as expanding clouds of gas and shock waves produce knots enriched with heavy elements forged in the stellar core or during the explosion, creating pockets of material that differ from the surrounding medium and eventually contribute to the formation of new stars, planets, and even the building blocks of life. Demonstrating how the death of one star enriches future generations and maintains the chemical diversity of galaxies. Cold molecular hydrogen in galaxies, often invisible due to its lack of strong radiation, forms the raw material for star formation, and astronomers detect it indirectly through accompanying molecules such as carbon monoxide. These reservoirs, especially abundant in rapidly growing galaxies, can span large regions and fuel star formation over millions of years, with their presence or absence determining whether a galaxy remains active or enters a quieter phase. And mapping these hidden gas components provides crucial insight into galactic evolution from mergers to internal dynamics, illustrating how the unseen plays a central role in shaping cosmic structures. In dense stellar environments, stellar collisions can produce unusually massive and luminous stars, where the outer layers of close-passing stars merge to create a single, hotter, brighter object capable of faster fusion. And these collision-born stars, identifiable by their intense blue light and apparent youth relative to neighboring stars, highlight that not all stars form through simple gravitational collapse. Some arise from violent but creative encounters in crowded clusters, revealing the diversity of stellar formation processes. Extreme temperature differences on planets occur when bodies orbit close to their stars, particularly if they are tidally locked, with one side perpetually facing the star and the other in darkness, producing searing day sides and frigid night sides, with intense winds transporting heat and creating complex climatic patterns influenced by altitude, cloud formation, and atmospheric composition, providing researchers with a laboratory for understanding energy circulation and climate stability in extreme environments, demonstrating that even within a single planetary system, conditions can vary dramatically. In the outskirts of galaxies, stars orbit near escape velocity, where the gravitational pull weakens with distance, yet the presence of dark matter maintains their binding, and these distant stars trace the extent of the galactic halo, revealing the influence of unseen mass and allowing astronomers to map the growth and structure of galaxies, where the interplay of visible and invisible matter defines the true scale of galactic influence. Black holes, though themselves invisible, emit soft X-rays as matter spirals inward, forming accretion disks heated to millions of degrees. As gas from nearby stars or clouds accelerates and compresses, the inner regions radiate intensely, providing detectable signals that reveal the dynamics near these extreme objects, highlighting the complex interactions between matter and gravity, and serving as laboratories for understanding energy transfer, relativistic effects, and the limits of physics. Together, these phenomena, from intergalactic starlight, cometary jets, galactic winds, high-speed stars, molten exoplanets, supernova remnants, molecular hydrogen reservoirs, collision-borne stars, tidally locked planets, outer halo stars, and accreting black holes, illustrate the extraordinary diversity and interconnectedness of the universe, showing how matter and energy flow through multiple scales, how creation and destruction coexist, and how observing these processes allows scientists to reconstruct the past, understand the present, and predict the evolution of cosmic structures over billions of years, revealing a universe that is dynamic, interwoven, and governed by both visible and invisible forces acting in concert to shape the galaxies, stars, planets, and interstellar matter that fill space with light, motion, and structure. These emissions help scientists study conditions close to points where gravity becomes overwhelming, as the pattern, intensity, and variability of radiation reveal how quickly matter is falling inward and how the accretion disk is structured, with fluctuations in brightness indicating turbulence, magnetic disturbances, or changes in the inflow of surrounding gas. And observing soft X-rays provides rare insight into environments just outside the boundary of no return, offering a window into the final moments of matter before it disappears forever. Meanwhile, complex organic molecules can form in cold, dark nebulae deep within interstellar clouds where starlight barely penetrates, and temperatures are low enough for slow, exotic chemistry to unfold over long periods, with dust grains coated in thin layers of ice serving as miniature laboratories where atoms accumulate and react, while cosmic rays and faint ultraviolet light penetrate just enough to trigger interactions among molecules trapped in the ice, producing intricate organic structures including chains, rings, and branching arrangements of carbon-rich compounds, which are later released into the surrounding gas as the nebula collapses and warms, enriching the material from which new stars and planets form and providing early evidence that the basic ingredients for biological chemistry can emerge long before planets exist. Some exoplanet atmospheres expand into enormous, puffy envelopes in extreme close-orbit conditions, where intense stellar radiation heats outer layers so dramatically that they swell far beyond the planet's surface, forming diffuse structures shaped by stellar winds and gravity that may escape gradually into space as long trails of material following the planet along its orbit, and transit observations reveal the size, composition, and temperature of these inflated atmospheres, providing clues about the planet's history and the effects of intense irradiation, illustrating how extreme heating can dramatically reshape planetary envelopes. The earliest galaxies formed in the young, chaotic universe, mere hundreds of millions of years after the Big Bang, as matter clumped under gravity to create small, irregular structures filled with rapidly forming stars whose intense radiation reshaped their surroundings, and frequent collisions between these nascent galaxies mixed gas and triggered bursts of star formation that consumed material at astonishing rates. In a cosmos still lacking the heavy elements produced by later generations of stars, leaving these first galaxies composed of pristine gas with physical behaviors distinct from enriched clouds observed today, and by studying distant galaxies, astronomers can peer back in time to understand the chaotic beginnings that ultimately led to the formation of modern galaxies. Some stars form in metal-poor environments that closely resemble conditions in the early universe, where gas contains very few elements heavier than helium, and the resulting stars behave differently because the scarcity of metals influences cooling, internal structure, and nuclear reaction rates, often shining with unusual colors or displaying chemical signatures that stand out from more typical populations, allowing scientists to test theories of stellar evolution under primordial conditions, and to trace the gradual enrichment of the cosmos with heavier elements through successive generations of star formation. Galactic bars provide another mechanism for shaping galactic evolution, funneling gas from the outer disk towards central star-forming regions, where pressures rise and dense pockets ignite intense star formation, producing bright clusters that illuminate surrounding clouds, while the bar itself evolves over time, influencing rotation, gas circulation, and bulge development, showing how internal structures regulate material flows and sustain cycles of activity that transform a galaxy's appearance over millions of years. Planets can also inhabit extreme gravitational environments, including systems with multiple stars, where wide looping orbits around two or more suns require delicate balancing of gravitational forces, producing trajectories that shift as stars move relative to one another and subjecting the planet to cycles of varying illumination. With fluctuating climates that reveal the resilience of planetary formation in dynamic multistar systems and demonstrate that stable planetary orbits can persist, even under complex stellar choreography. Cosmic shock fronts energize particles to extreme velocities when fast-moving matter collides with slower gas or dust, creating boundaries where compression generates surges of heat and radiation. These occur in supernova remnants, galactic winds, and regions impacted by jets from compact objects, where particles repeatedly bounce between areas of differing magnetic fields, gaining energy with each pass, sometimes approaching relativistic speeds, contributing to the cosmic ray population that travels across interstellar and intergalactic space. And by analyzing emission from shock fronts, scientists uncover how energy is transferred in extreme conditions and how high-energy particles influence their surroundings, affecting gas distribution and driving the evolution of galaxies. Some galaxies shine brightly in radio wavelengths due to energetic processes, including synchrotron radiation from relativistic electrons spiraling along magnetic fields, highlighting dynamic interactions within galactic nuclei, supernova remnants, and regions of starburst activity, while the combined radio emission traces both recent activity and the long-term accumulation of energetic particles, providing insight into magnetic field structures and the flow of energy across galactic scales, and revealing the interplay between star formation, stellar deaths, and the acceleration of particles to high energies. These processes are further complemented by observations of intergalactic light, where stars stripped from their original galaxies during collisions continue to shine in isolation, producing a faint glow between galaxy clusters that acts as a quiet record of cosmic interactions over billions of years, enabling astronomers to reconstruct mergers, collisions, and cannibalistic events that shaped large-scale structures. In our own solar system, comets illustrate the effects of heat and material response on a smaller scale, as icy surfaces vaporize under stellar illumination, creating jets of dust and gas that form bright comas and tails, while the behavior of these jets, rotation, pulsing, and shifting, reveals the comet's spin and internal structure, and the materials expelled contribute to understanding the primordial makeup of the solar system. Galactic winds, generated by massive stars and supernova explosions, can expel gas from galaxies, quenching star formation by reducing the availability of dense molecular clouds, reshaping galactic morphology, and creating cavities and channels that trace the paths of escaping material, demonstrating how feedback mechanisms regulate the balance between creation and destruction. Stars can be accelerated to high velocities after gravitational interactions with clusters, binary companions, or spiral arms, occasionally gaining enough speed to escape the galaxy entirely, or altering trajectories so they travel far from their birthplace. And by mapping these wandering stars, astronomers gain insight into the dynamic forces shaping the Milky Way's structure. Exoplanets in extreme environments may host molten surfaces, forming oceans of liquid rock with vaporized mineral atmospheres that condense, fall as rain, and circulate across the planet, while supernova remnants distribute heavy elements into space, contributing to new generations of stars and planets, and reservoirs of cold molecular hydrogen fuel prolonged star formation in galaxies. With the presence or absence of this hidden gas determining whether a galaxy remains active or becomes quiescent. Stellar collisions in dense clusters can produce unusually massive, luminous stars, while planets tidally locked to stars experience extreme temperature gradients between day and night, creating complex atmospheric circulation, and stars in outer galactic regions orbit near escape velocity, constrained by dark matter halos. Accreting black holes emit soft X-rays as matter spirals inward, providing crucial information about extreme gravitational environments, while organic molecules form in dark nebulae on icy dust grains, and exoplanet atmospheres expand dramatically under intense radiation, creating puffy envelopes that extend far from the planet, shaped by stellar winds and gravity. The earliest galaxies were small, irregular, and rapidly evolving, forming stars in pristine, metal-poor conditions and frequently merging, while galactic bars funnel gas inward to sustain central star formation, and planets can follow complex orbits and multi-star systems, maintaining stability despite fluctuating illumination, and cosmic shock fronts accelerate particles to relativistic speeds, contributing to cosmic rays and galactic evolution, with radio emissions tracing energetic processes. Together, these phenomena illustrate a universe in which matter, energy, and radiation interact across scales, from microscopic chemistry in dark clouds to large-scale galactic dynamics, revealing the intricate web of processes that govern the formation, evolution, and ultimate fate of stars, planets, and galaxies, while highlighting the interplay between visible and invisible forces, the recycling of matter, and the continuous transformation of the cosmos over billions of years. In many galaxies, certain regions produce strong emissions detectable in the radio part of the spectrum, often arising from electrons moving at high velocities through magnetic fields, generating synchrotron radiation that unveils energetic activity near jets, supernova remnants, or dense star-forming regions, while in some galaxies, central black holes accelerate particles that produce radio waves extending across thousands of light-years, allowing astronomers to peer through obscuring dust that blocks visible light and revealing hidden structures deep within the galactic interior, with careful mapping of these emissions uncovering motion patterns, traces of past explosions, and the influence of jets that stretch far beyond the visible disk, offering a deeper understanding of the physical forces shaping galaxies over cosmic time. Dusty tori around active galactic nuclei further conceal their central engines, as supermassive black holes feed on surrounding material and release immense energy, yet thick rings of gas and dust encircle these cores, absorbing high-energy radiation and re-emitting it at longer wavelengths to produce signatures that betray the presence of hidden activity. While the shape and thickness of these tori influence a galaxy's appearance across multiple wavelengths, helping scientists understand how central black holes grow, interact with their surroundings, and regulate the brightness of active galaxies, acting as gateways that control how much energy escapes into the galaxy. On certain cold worlds, subsurface lakes may exist between layers of rock and ice, where sunlight is insufficient to sustain liquid water at the surface, yet heat from the planetary interior melts pockets of ice deep beneath the crust, which expand into hidden reservoirs insulated by overlying layers that maintain pressure and prevent freezing despite sub-zero temperatures above, with minerals dissolving into the liquid to create chemically rich environments, while tidal forces from nearby moons or the parent planet stir the interior, maintaining a delicate balance between freezing and melting, allowing these lakes to persist over extremely long periods, shielded from radiation and surface turbulence, offering potential habitats for complex chemistry or even primitive biological processes, demonstrating that liquid water, a key ingredient for life, may be more widespread than surface observations alone suggest. Intergalactic stars, flung far from their original galaxies by tidal stripping during gravitational encounters, drift alone through the vast darkness between galaxies, their motions tracing past collisions that scattered them from galactic outskirts, while their faint light contributes to the soft glow between clusters, and their chemical compositions provide clues about the galaxies that once held them. Each star serving as a relic of dramatic cosmic events and carrying a quiet but enduring record of forces strong enough to unbind it from its home. Massive stars produce powerful stellar winds, intense streams of charged particles racing outward at tremendous speeds, sweeping aside gas and dust to carve enormous bubbles in the interstellar medium, which may span dozens of light years, with glowing edges where compressed material heats under the star's radiation, while inside the cavity, gas becomes thin and hot, shaped by the continuous outflow, and the bubble can grow, deform, or split depending on environmental conditions, with observations revealing how massive stars influence their surroundings and regulate star formation in nearby regions, preserving a record of energetic interactions with the interstellar landscape. Protostars accrete material through swirling disks of gas and dust, as gravity draws matter inward toward a central object, forming flattened disks rather than direct infall, where collisions and interactions gradually remove rotational energy and allow gas and dust to spiral inward, while some portions clump together to eventually become planets or smaller bodies. And jets emerging from the poles carry away angular momentum, shaping the surrounding cloud, the smooth inward flow of material within these disks marks one of the most crucial stages in the birth of stars across galaxies, revealing the mechanisms by which early stars and planets form and evolve, and demonstrating the intricate balance of forces that govern matter under gravity, radiation, and magnetic fields. Galactic processes continue on larger scales, with strong radio emissions highlighting regions where energetic electrons trace magnetic structures, revealing supernova remnants and jets, while dusty tori around active nuclei regulate the escape of radiation from supermassive black holes and influence the appearance and evolution of galaxies, showing how feedback processes control star formation and energy distribution. Subsurface water, hidden beneath ice and rock on distant planets, illustrates the potential for life-supporting chemistry far beyond habitable zones, while intergalactic stars record the violent history of galactic interactions and tidal forces, moving through vast emptiness yet carrying chemical clues from their parent galaxies. Stellar winds carve monumental cavities, shaping the interstellar medium, while protostellar disks organize material into stars and planetary systems, with jets maintaining angular momentum and guiding accretion. Together, these phenomena reveal a universe where matter, energy, and gravity interact across scales, from tiny icy grains in dark nebulae to entire galaxies, showing how stars are born, evolve, die, and influence their surroundings, how planets may sustain hidden oceans, and how galaxies form, interact, and redistribute matter through collisions, feedback, and radiation, offering a continuous, interconnected view of cosmic evolution across space and time. Some galaxies experience bursts of star formation that consume gas rapidly, as during certain periods in a galaxy's evolution, conditions may align to trigger widespread creation of new stars, with collisions involving smaller galaxies, inflows of fresh gas, or internal instabilities compressing material into dense pockets where star formation ignites at an accelerated pace, causing starburst regions to shine brightly as thousands of young stars heat and illuminate surrounding clouds, releasing strong winds and intense radiation that eventually disrupt the very clouds that birth them, pushing gas outward or heating it to the point where it can no longer collapse, slowing the starburst and allowing it to fade, a cycle that can transform the appearance of a galaxy over relatively short cosmic timescales. While studying these bursts reveals how galaxies grow, change, and regulate their own star-forming activity over millions of years, as high-energy photons from young stars ionize nearby nebulae, with massive newborn stars emitting streams of ultraviolet light that strike surrounding hydrogen-rich gas, knocking electrons free to create glowing zones of ionized material, tracing the movement of radiation through clouds, carving shapes, opening cavities, and generating pressures that reshape the environment, leaving the nebula as a record of the early relationship between newborn stars and the material from which they formed, serving as luminous signposts of stellar youth. Throughout the galaxy, while on certain moons, complex geology arises from internal heating, generated by tidal forces, radioactive decay, or residual formation energy, melting pockets of rock or maintaining layers of soft, shifting material, producing cracks, ridges, and varied terrains on the surface as the interior circulates and expands or contracts. With plumes of gas or icy particles rising from fissures to reveal the hidden chemistry beneath, the patterns of fractures and smooth plains. Documenting long histories of tectonic and volcanic processes, demonstrating that even small worlds can host dynamic interiors driven by energy sources far below the surface, while black hole accretion flares provide dramatic variability over short timescales, as gas spirals toward a black hole in clumps that collide, twist, or interact with magnetic fields, producing sudden bursts of energy observable as rapid flares, whose timing and intensity reveal conditions near the event horizon, including turbulence, temperature gradients, and magnetic field behavior, each flare becoming a fleeting signal from the edge of one of the universe's most enigmatic objects, while distant exoplanets may orbit so far from their stars that their years last centuries, moving along immense paths where weak gravitational pulls result in slow travel and cold, dark conditions, with faint starlight providing minimal illumination, and long orbital cycles creating environments unlike those found closer in, with the study of these distant worlds revealing insights into planetary system organization, disk dispersal, planetary migration, and how outer regions evolve over time, while relics of ancient star clusters drift through the galaxy as faint luminous traces, once tightly bound clusters gradually losing members to galactic gravity, with their stars spreading along extended paths that trace original orbits. Detectable through precise motion and chemical composition studies, each star carrying elemental signatures of its birth environment, allowing astronomers to reconstruct the shapes, lifetimes, and dispersal of clusters no longer existing as unified groups, showing how the galaxy's gravitational field stretches and disperses smaller structures, these drifting remnants quietly recording the ancient gatherings of stars that once shone brightly but have since been pulled apart by steady galactic tides. While drifting now into the quiet part of the night, where the rush of thoughts loosens and wakefulness softens, one has traveled through distant galaxies, ancient starlight, worlds of ice and fire, and cosmic landscapes unfolding gently around, allowing all to sink into the background like a fading tide, with nothing needed to remember or hold on to, the universe continuing its slow, patient motion without effort. Feeling the breath settle in the chest as if rising and falling with some distant cosmic rhythm, imagining stars thinning into a soft glow behind closed eyelids, a sense of safety and stillness pervading as one floats in a night that welcomes fully, each inhale gathering the last traces of the day, each exhale letting them drift away, with the promise of more journeys available whenever desired, soft stories, gentle science, and quiet wonders present to ease one toward rest, allowing letting go, slowing thoughts, deepening physical rest, mind becoming lighter and quieter, like a small moon settling into peaceful orbit, with nothing required to do or destination to reach, only the calm gathering, patient and warm, settling into it now, letting it carry one the rest of the way. Good night.